Welcome to G Fun Facts Online. Imagine building the most powerful computer ever conceived, capable of solving problems that would take today's supercomputers billions of years. This is the promise of a quantum computer. But there's a catch. The fundamental building blocks of this machine, the qubits, are incredibly fragile. The slightest vibration or temperature change can corrupt an entire calculation. To solve this, scientists developed quantum error correction, a way of bundling many fragile physical qubits together to create a single, robust logical qubit. But this creates a paradox. The very techniques used for error correction, called Clifford operations, are not powerful enough on their own to run the most interesting quantum algorithms. A quantum computer using only these operations can be perfectly simulated by a regular classical computer, defeating the whole purpose. To unlock true quantum power, we need something extra. We need a spark of magic. This magic comes in the form of special quantum states called magic states. They are the non-classical fuel, the secret sauce that elevates a quantum computer beyond what any classical machine can do. The problem? Creating these magic states is a messy, noisy process. The raw states produced by real-world quantum hardware are too error-prone to be useful. This brings us to the central challenge: magic state distillation. It's a purification process, first proposed in 2004, that takes many noisy, low-quality magic states and distills them into a smaller number of high-quality, near-perfect ones. Think of it like refining crude oil into high-octane jet fuel. For nearly 2 decades, this distillation process was seen as the Achilles heel of quantum computing, a process so resource-hungry, it threatened to make building a useful quantum computer impossibly expensive. But that picture is changing dramatically. Today, we're going to explore the world of magic state distillation, from its brute force beginnings to a series of recent quantum leaps that are turning this bottleneck into a solvable engineering problem. To understand the quest for better distillation, we first have to understand how you even measure magic. This is where the resource theory of magic comes in. It's a formal framework that defines what is free and what is costly in the quantum world. The free stuff includes preparing simple stabilizer states and performing those limited Clifford operations we mentioned earlier. The costly resources are the magic states themselves, like the crucial T-state, which enables universal computation. The goal of distillation, then, is to use only free operations to turn a bunch of low-quality resource states into a few high-quality ones. To measure how well a protocol does this, researchers developed several mathematical tools. The first is called the robustness of magic. It tells you how much non-magical stabilizer stuff you'd have to mix into a magic state to completely destroy its magic. It's a measure of resilience. Another measure is thamma, from the Greek word for wonder. It's a benchmark that tells you how close a distillation protocol is to the absolute best-case scenario allowed by the laws of physics. These tools aren't just academic. They're the rulers used to judge every new distillation technique. They also revealed a strange phenomenon: bound magic states. These are states that contain magic, but for complex reasons, cannot be distilled into pure, usable magic states, much like how some entangled states cannot be purified. With these tools in hand, the scientific community began designing the first distillation protocols. This was the brute force era. The early methods established that distillation was theoretically possible, but at a staggering cost. These protocols work by encoding noisy magic states into a quantum error-correcting code, performing a key operation, and then checking for errors. If an error is detected, the whole thing is thrown out. The foundational protocol, from Sergei Bravyi and Alexei Kitaev, is the famous 15-to-1 routine. It takes 15 noisy copies of a T-state as input. These are used to power a T-gate on a logical qubit encoded in a special 15-qubit code. Afterwards, the machine checks for errors. If there are none, it outputs a single, much higher fidelity T-state. The power of this protocol is its error suppression. If the input states have an error rate of, say, 1%, the output state has an error rate on the order of 1 in a million. This is a cubic improvement. The obvious trade-off is the cost. You burn 15 states to get just one. Bravi and Kitaev also developed a 5-to-1 protocol. It's less powerful, only squaring the error rate instead of cubing it, but its lower input cost makes it useful in certain situations. Another team, Meyer, Easton, and Nil, introduced a 10-to-2 protocol, offering a different balance of resources and performance. The existence of these different recipes led to the idea of concatenation. You could build complex, multi-stage distillation factories. You might first use the more efficient 10-to-2 protocol to do a rough purification, and then feed those improved states into the more powerful 15-to-1 protocol for the final polishing stage. Later work by Bravi and Jungwon Ha found a systematic way to discover new protocols using something called triorthogonal matrices, further improving efficiency. But even with these clever ideas, the overall picture was sobering. These distillation factories were estimated to consume over 90% of a fault-tolerant quantum computer's total resources. The sheer number of qubits and operational steps required was immense. For quantum computing to become practical, something had to give. This set the stage for a true quantum leap in distillation methods. The narrative of magic state distillation being an insurmountable bottleneck is now being completely rewritten. The first major leap was a landmark experiment reported in 2025 by a collaboration including Quera Computing and Harvard. For the first time ever, they demonstrated magic state distillation working not just on fragile physical qubits, but on robust, error-corrected logical qubits. Using their Gemini neutral atom quantum computer, the team took 5 imperfect logical magic states and successfully distilled them into a single, higher fidelity logical magic state. They performed the experiment on 2 types of logical qubits, a DIST-ANCE3 code that can correct 1 error, and a more powerful distance 5 code that can correct 2. The results were clear. The final distilled state was significantly better than any of the inputs. Crucially, the process worked even better on the more robust distance 5 code. This was a monumental achievement. It was the first real-world proof that the entire theoretical structure of fault-tolerant computing, combining logical qubits with magic state distillation, actually holds up. It changed the fundamental question from "can we build these computers at all?" to "how can we make them truly useful and efficient?" While that experiment validated the principle, other researchers were tackling the enormous resource overhead of the traditional factory model. One of the most exciting new paradigms is called magic state cultivation, pioneered by Craig Gidney and his colleagues at Google Quantum AI. Cultivation flips the old model on its head. Instead of a many-to-one process, cultivation is a one-improving process. It starts with a single magic state and gradually grows its reliability. The process has 3 stages. First is injection, where a single magic state is prepared and encoded into a small, low-distance error-correcting code. The second, core stage, is cultivation. The patch of code protecting the state is incrementally grown in size. At each step, special checks are performed to verify the state's integrity. This stage relies heavily on post-selection. If any error is detected at any point, the entire state is thrown out and the process restarts from scratch. This gradual, iterative improvement of a single state is what gives the method its name. The final stage is escape. Once the state is highly purified within its small code, it's transferred into a large, high-distance surface code where it can be safely stored for use in an algorithm. The key difference is that cultivation happens inside a growing code, while traditional distillation happens on top of fixed-size logical qubits. By cleverly managing this process, cultivation promises an order-of-magnitude reduction in the total resources required, specifically the space-time volume, which is the number of qubits multiplied by the time they are used. Its efficiency is also incredibly sensitive to hardware improvements. Having the physical error rate of the machine could lead to a 30-fold improvement in the final magic state's quality, while simultaneously reducing the cost by a factor of 10. Magic state cultivation represents a shift from brute force purification to a more organic, resource-aware method of growing quality. At the same time, another highly efficient method called zero-level distillation emerged from researchers at Osaka University. This approach also aims to slash overhead, but through a different mechanism. The core idea is to perform the entire purification process at the physical qubit level, the 0th level, before the state is ever encoded into the large, final code used for the main computation. The protocol goes like this. First, a noisy magic state is encoded into a small, efficient 7-qubit code called the Steen code. Next, a verification check, known as a Hadamard test, is performed on this encoded state. If the state passes the test, it isn't decoded. Instead, it is directly teleported into a more robust surface code using a technique called lattice surgery. This effectively transfers the now purified logical state from its temporary Steen code home to the more permanent and widely used surface code architecture. By avoiding the use of multiple large logical qubits during the distillation process itself, zero-level distillation achieves a substantial reduction in both qubit count and time. These breakthroughs, the logical qubit experiment, cultivation, and zero-level distillation, have painted a much brighter future. The once daunting mountain of resource overhead for magic state distillation now looks more like a manageable, though still steep, hill. However, significant challenges remain. One of the most critical hurdles is the impact of imperfect operations. Our theoretical models often assume the free Clifford gates and measurements are perfect, with all noise confined to the input magic states. In reality, every component is faulty. Even low levels of noise in the checking process can degrade performance and limit how much purification is possible. Future protocols must be designed to be robust against this real-world noise. Another vital area is the connection to hardware. The optimal distillation strategy isn't one-size-fits-all. Magic state cultivation, for example, might be a natural fit for trapped ion or neutral atom computers, where qubits can interact over long distances. Other protocols optimized for nearest neighbor interactions are better suited for superconducting qubit designs. The future of optimal distillation lies in this co-design, tailoring protocols to the specific physical platform. Finally, the theoretical frontier continues to advance. Researchers are searching for the absolute limits of distillation efficiency, with some proposals even pointing toward protocols with constant overhead, where the number of input states wouldn't need to grow with the desired accuracy. The journey to perfect magic state distillation is a story of profound theory meeting ingenious engineering and experimental validation. The quantum leap we're witnessing is not a single event, but a continuous process of innovation. The progress from brute force factories to the elegant resource-aware methods of today has been immense. And it makes it clear that the magic required for universal quantum computation is no longer a fantasy, but a resource we are learning to distill, cultivate, and control with ever greater precision. Mastering this process will be the pivotal moment that turns the dream of a fault-tolerant quantum computer into a world-changing reality.